E1 unimolecular elimination reaction. In this case, if we take an example of tertiary butyl bromide which react with NaOH, we get isobutylene along with water and Br negative. According to rate law, rate of reaction depends on only tertiary butyl bromide. It is independent of the concentration of base. That means in the rate determining step, only tertiary butyl bromide is involved. Let's look at its mechanism. In this reaction, first of all, the C-Br bond breaking takes place. So in the first transition state, C-Br bond start breaking. This is first transition state, and we get carbocation along with Br negative. You know this is planar carbocation. Now in this planar carbocation, hydrogen from the adjacent carbon interact with OH negative. This is slow step, first step. This is fast. Now transition state is OH become partial negative, become partial positive, and finally we get this product along with H2O. So this is second transition state and this one is first transition state. So in the first transition state, carbocation is formed. So this formation of carbocation depends on how easily this C-Br bond breaking takes place and stability of the carbocation. These are the two factors which decides the E1 reaction. Stability of the carbocation and ability of leaving group. If it is good, then E1 reaction is easily taking place. The order of reactivity of alkyl halide in E1, again same tertiary, secondary, primary. Tertiary alkyl halide is most reactive, then secondary, then primary. As carbocation is formed as the reaction intermediate, so rearrangement can take place. That means in E1 reaction, a rearranged product may be formed. Now if we have an option of choosing, again two types of beta hydrogen. Now in E1 mechanism, ZJ product always is the major product. ZJ product is the major product because carbocation is formed in this reaction. So products are CH3, CH2, CH double bond, or this one is major product and this is minor product. This is ZJ product. ZJ product is always major product in E1 reaction. Now let's take an example of rearranged product. Okay, this is the example. Now first, C-Br bond breaking takes place. So when we break this bond, we get this is secondary carbocation. Whenever secondary or primary carbocation is adjacent to tertiary or quaternary carbon, then 1,2 hydride and 1,2 methyl shift takes place. This is quaternary carbon, so 1,2 methyl shift takes place, and when this methyl group shift, we get tertiary carbocation which is more stable than secondary carbocation. Remove the H plus ion in the presence of OH negative. So water is removed and we get this alkene. So this is a rearranged product. That means in even reaction we can get a rearranged product. It can form simple product when H is removed from here, it is double bond, but that is minor product, and this one is major. This carbocation is formed, and in the presence of base OH negative ion, water is removed, H from here, so we get this product, but this is minor product. If we draw potential energy level diagram for this reaction, potential energy versus progress of the reaction, then it is like this. These are reactants. This is first transition state, this is second transition state, and carbocation is the reaction intermediate. For the reaction, the product formed along with water and Br negative. So in even reaction, carbocation is formed as reaction intermediate. Reactivity order, alkyl halides. So for even reaction, reactivity order of alkyl halides is in the order tertiary benzyl halide, which is greater than or equal to tertiary allyl halides, which is greater than secondary benzyl halide, which is slightly greater than or equal to secondary allyl halides, which is equal to tertiary alkyl halide. Then it is turn of primary benzyl halide, which is slightly greater than or equal to primary allyl halide, equal to secondary alkyl halide, and then primary alkyl halide, and at the end vinyl halide, because in vinyl halide, you know, breaking of CX bond is very difficult because it has double bond character due to plus R effect of chlorine. Chlorine and carbon bond has double bond character due to resonance. Let's take a case of this compound in the presence of aqueous NaOH, OH negative. First of all, we get CH3 CH double bond, CH2 CH positive, CH3. Now this double bond and positive charge, they are separated by two single bonds, but this hydrogen is allylic hydrogen. So if we shift this hydrogen with electron pair to this is called 1,2 hydride shift, then we get allyl carbocation, and you know allyl carbocation is more stable than the secondary carbocation. That's why 1,2 hydride shift takes place, or we can say it provides the driving force for this shift, 1,2 hydride shift. And then there is a removal of hydrogen adjacent to it, so we get alkene, which is more stable, and it is formed as major product because it is a conjugated diene, and conjugated dienes are more stable than isolated dienes. This is major product, and minor product is, this is the minor product. Now in even reaction, as I said earlier, that Sergev product is the major product, but there is one limitation. If beta carbon on one side is sterically hindered, it is highly substituted, then see this carbocation, there are two options, either least hindered, hydrogens are removed, or more hindered. This carbocation is formed, so normal product is this, and if we remove this, we get this is Serge product, Hoffman product, and Hoffman product is major product. In this case, it is because of steric hindrance. Because of steric reason, we get Hoffman product even in E1 reaction. So keep in mind, there is one case when one of the carbon, beta carbon, is sterically hindered, then we get Hoffman product as the major product in E1 reaction. Otherwise, in all the other cases, we get Serge product as the major product. In even reactions, carbocation is formed, and tertiary carbocation is more stable than secondary than primary. So order of reactivity is for halides, it is tertiary, secondary, primary. Second, what about strength of the base or concentration of the base? So this reaction, a rate of even reaction depends upon only substrate. Base is not involved in the rate determining step. That's why strength of the base and concentration of the base has no role to play in the rate of even reaction. Third, leaving group. If an ion is least basic and more polarizable, that is a good leaving group and increase the reactivity. For example, I negative, Br negative, Cl negative, F negative. This is the order of reactivity of alkyl halides. Iodides are more reactive than bromides. Bromides are more reactive than chlorides and then fluorides. That means iodide remove easily. What about solvent? So as carbocation is formed as a reaction intermediate, that is a more polar solvent, favor this reaction. So rate of even reaction is proportional to polarity of solvent. As polarity of solvent increases, a rate of even reaction increases. And what about stereochemistry? They are non-stereospecific because both the elimination takes place. Syn as well as anti elimination. That's why no specific product is formed. They are non-stereo selective, though they are regioselective, because Serge product is the major product in most of the even reactions.